Hey everyone, hope we're going well. So, even though it's week 10 and technically this is not a teaching week, I am going to be going through some revision of the content that we've been going through so far this term. And this is just to make sure that you understand what's expected of you, what stuff you're expected to demonstrate for any exams that we end up having and tests that we're going to be having as well. Okay, so the first thing we're going to be looking at is trigonometry, which we covered at the start of the year. And I'm going to be going through the SCSA guidelines. So you can get those at this website. So I will be putting these notes up online so you can get access to them at the end of the week. Or if you wanted to get access to them just by searching online, search for the line SCSA 11 methods just on the internet. Look under the syllabus menu and it'll give you the year 11 syllabus there. And that contains all the things you're expected to know that you're expected to be able to demonstrate for the year 11 methods course. Okay, so now let's have a look at what you're expected to do. So first up, just let me get myself set up here. So there's a few basic ones. We're just going to skip straight to the cosine and sine rules section. It starts off pretty straightforwardly, and it's got the word review here. Review means it's basically stuff you're expected to know already from previous years. And it says review sine, cosine, and tangent as ratios of side lengths in right-angled triangles. So this pretty straightforwardly is SOHCA. Now we should all be familiar with SOHCA. Now if you are having trouble with SOHCA, and it's totally understandable that you might be having trouble with SOHCA, there is actually a, where are we? So there's a good online activity. If you do, it is a site called Transum. And the thing about Transum, come on, Kitty. The thing about Transum is that it does these sort of automatic self-marking activities. If you do a web search for Transum Advanced Trigonometry, like we can see there, you should be able to get access to that, and it's got some practice questions that we can do there. And there's different ones for different forms of the rule. We've got the cosine rule and the area formula in there as well. So there are ones that we can have a look at there. Okay, so back to this one. Now, so we've got SOHCA. Now for SOHCA, it's pretty straightforward, but I'm just going to write it here anyway. If we've got our typical right-angled triangle, and we need to be able to recognize right-angled triangles in a variety of different ways. So if this is our angle theta here, it's not helping. So if that's our angle theta there, that is our opposite, that's our adjacent, and that is our hypotenuse there. And so we'd have sine theta equals opposite on hypotenuse, and also the other stuff, like we would expect to know that hypotenuse is equal to opposite over sine theta, and opposite equals h sine theta. And to be able to use the inverse sine rule to be able to work that out. So that would be inverse sine opposite, inverse sine opposite on hypotenuse is going to give us our theta. So those are the things that we're expected to be able to do. I'm not going to list out all of them for sine, cos, and tan because we should all be able to do those without too much trouble. And so that's just the first one, that's SOHCA. I would strongly recommend getting some practice in if you are having any issues with that. It's a really important one to make sure that you're just fluent with and able to do. There's plenty of online opportunities to practice SOHCA. If you just look for them online, there are things that can show us. So that is 1.2.1, just SOHCA. 1.2.2 is understanding the unit circle definition of cos theta, sine theta, and tan theta. So that's basically if I've got my circle, and I'm going to do it in red here. Okay. So now if I've got my circle there, let's actually move that a little bit better. I'm sure I can get a better middle than that. Yeah, okay, that'll do for now. So basically, if I've got this point here on my circle, it has an x coordinate, it has a y coordinate. The x coordinate is going to be, if this is the angle theta, the x coordinate is going to be cos theta, and the y coordinate is going to be sine theta. And so that's the unit definition of the unit circle. So basically that can also mean that if we've got an angle going out there, then we can end up with different values. And we also always measure the angle counterclockwise from this line here. So this one will be an angle between 90 and 180 degrees. And that would result in the cosine theta, because that's the x coordinate there. That would result in that one being negative. Likewise, if we were down here, both the x and y coordinates would be negative, and if we were down here, the x coordinate would be positive, but the y one would be negative down there. So depending on which quadrant you're in, and the quadrants are 1, 2, 3, and 4 is how we number those quadrants. Depending on which quadrant you have, you can end up with different situations where some are positive, some are negative for cosine theta and sine theta. Now, we're going to go into this in more detail at the start of term 2, because there's some relevant sort of information, and hopefully it'll become a bit more obvious as we go. So, periodicity basically means that every 360 degrees we repeat ourselves. So if sine 30 degrees, or sine 30 is equal to a half, which we should all know, sine of 390 is also equal to a half. These are all degrees. And sine 750 degrees is also equal to a half, because I'm just adding 360 to each of these, and in each case we should end up with a half, because it just repeats itself as it goes around in circles. So that's the unit circle definition. The relationship between the angle of inclination of a line and the gradient of that line. So that is involving tan theta. So tan theta, in this particular situation, in fact, I'll just write it underneath. So tan theta is, remember that's, according to SOHCA, it is opposite over adjacent, which is going to be y over x, which is actually, where are we, sine theta over cos theta. That's actually the definition of what tan is. But there's another thing that's important about tan theta, is that it is also rise over run. Because remember, the amount it goes up in y is its rise, the amount it goes across in x is its run. So if tan theta is rise over run, that is going to be the gradient. And there we have it. So that is the relationship between the angle of inclination of a line and the gradient of that line. It's just that tan theta is equal to the gradient. It's a pretty simple one, that one. The next one is fairly complex. You got to know use the cosine and sine rules, including consideration of the ambiguous case and this formula, area equals half BC sine A, for the area of a triangle. Now there's a lot of this one, there's a lot tied up in this one. Let me just a sec. Need a bit more vertical space here. So this is all we learnt about non-right angled triangles. We also covered that a little bit in, where is it? So we also covered that a little bit in year 10, but we've got our standard, if we have our, where are we? We can imagine our triangle, a non-right angled triangle looking a bit like this. We have our three sides, A, B, and C. And then we have our corresponding angles, capital A, capital B, and capital C. And this is just telling us that the cosine rule, which is c squared equals a squared plus b squared, take 2ab cos c. Remember that that's big C, so that's the angle. So that'll tell us that'll be able to let us solve this if we know two sides and the angle between them, and then that'll let us work out the other side. Or if we know the three sides, then or if we know three sides, we can work out the corresponding angle that we've got there. Actually, let's highlight these properly because it's got A, B, C, and we've got angle C. So if we happen to know two sides and the angle between them, then we can use the cosine rule there. Or if we know three sides, we can use the cosine rule as well. Yeah, so that's that one. Then we've got the sine rule. And that is, where is it? It's A over sine A equals B over sine B equals C over sine C. Though technically speaking, we don't ever really care about that third part of it. We just know that it's true that we can involve a third side if we want to, and we can repeatedly use the sine formula to work out all separate sides. Now we'll use the sine formula, and I'll use my purple pen to highlight that. So we'll use the sine rule if we ever have a pair. So if we happen to know a side and another side, a side and an angle there, and then we know one other thing, whatever it happens to be. Let's say we know this angle here. But if we happen to know a pair, an angle side pair, we can use the sine rule, provided we know at least one other thing. And then we can start to work out. So from this side angle pair and this one here, we could work out this one over here, this B. So that's what we've got there for our sine rule. And it also mentions something called the ambiguous case. So the ambiguous case. Now this ties back into our unit circle up here. And the thing about the unit circle, so let me get stuff set up over here. Yeah. So the thing about the unit circle is that if we've got an angle that's 180 degrees or over 180 degrees, if it's a sine angle, remember that sine is the y-axis here, we can't tell which way that angle is pointing, if it's less than 90 degrees or if it's greater than 90 degrees. What that means is that whenever you use inverse sine, you may get two answers. So there may be an acute or an obtuse answer to this one. So that is that's the ambiguous case there. And that's something to be really aware of, is that when you use inverse sine, whenever you use inverse sine on a triangle, there are two possible answers. That's just an important part of using this. And the last one, obviously, is our, so our last one is obviously the area, which is, write that in green over here, A equals half AB sine C. So that's if you know two sides and the angle between them, then you can find out the area of that triangle. It's, in fact, I won't use A because A is a bit ambiguous. It's not the angle A. So I'm going to write area. Area equals half AB sine C. Now, you should have all of these in your class pad. If you go to your E-activity, you should have all of your sine rule, your cosine rule, and as you can see in the sine rule up here, they don't actually give us the, hasn't actually given us here the C part, so I've crossed it off down here. So when I cross it off down here, that's pretty much what they do over here as well. And remember that whatever number you start with is going to be the number that it's going to give you that's closest to it. So let's say I start with 120 on this angle here, and I want to try and work out what the angle is going to be. I click solve, and it gives me an angle of 126. But if I started on 40 and clicked solve, it'll give me the acute angle of 53 degrees in there instead. So it can give you both of them, but you have to sort of give it a number that's fairly close to the result you want to get out. So that's what we've got there. Now, so that's in a nutshell, that is all of our cosine and sine rules, at least while working with degrees. And so next up, we've got circular measure and radian measure. Now, let's give myself a bit more space. When we're using circular measure and radian measure, remember that a number in degrees can be converted to radians. And the way that we convert it from degrees into radians is we basically multiply it by pi over 180. So you've got a large number here, you're effectively dividing it by 180 to get a much smaller number that we end up with for our radians. And likewise, when we go back, we would multiply by 180 over pi. And we get a number in radians that, or whatever our number in radians is, it becomes a much larger number when we convert it into degrees. So that's what we've got for that. Another thing is that a full 360 degrees is 2 pi radians. So 2 pi radians is 360 degrees. And we often talk about our angles as being a fraction as well. So this would normally be 45 degrees, but we would consider it, now we consider a semicircle or 180 degrees as pi. So 180 degrees would be pi. This is a quarter of the way to pi, so I consider it pi on 4. This is halfway to pi, this is pi on 2. If I had this is 120 degrees. That is 2/3 of the way to pi, 2 pi on 3. So these are things we should be thinking about when we're thinking about radian measure. Okay, but I think there's a point about that a bit further on. So we need to be able to convert between degrees and radians. So other things we've got, we have our circle formulas. We've got arc length. And now the actual reason why we do like to use radians is because it makes these sorts of formulas really easy. So if we already have converted our thing into radians, then our angle into radians, we can very easily work out what the arc length is. It's just the radius multiplied by that number. So if we've got pi on 4 radians and a radius of 3, then it will be 3 pi on 4 radians for our arc length. Length of chord. Oh yeah, I'm just gonna just draw a picture of a circle just so we can get an idea of what we're talking about. So if we had part of our circle like this, so our arc length is this part around the edge here. Our chord length, we've got a similar formula. That is 2r sine theta on 2. Now this one, because the theta is inside a sine there, then you can actually use degrees in this one because it's getting translated through the sine. So it's okay if you use degrees, just as long as your calculator is set to degrees for that one. So 2r sine theta on 2, and our arc length is the chord length is just that length there. It's going to be important to be able to get that quickly and easily. The area of a sector, so sector area. This is going to be r squared pi on 2, and the sector area obviously being the area of the entire thing up here. So that's sector area, that one there. In fact, let's make it yellow. I have reasons for making it yellow. So that's the sector area there. The last one is our segment area. And our segment area is a bit more complicated. It is r squared on 2 theta take sine theta. Now all of these, except for chord length, arc length, sector area, and segment area, all do need us to, let's just highlight that there. So we've got the green section there, that's the segment. All of these ones do require us to use radians. Anytime that our theta is outside of a sine function, so not that one, but anytime our theta is outside of a sine function, we need to use radians. So just got to make sure we're doing that. So these ones are just ones where it's really just good to practice them. There are lots of examples in your textbook and everything like that you can use to practice these. There's lots of practice examples in your in textbooks. There's practice exams that I've put up on Connect. But you'll need to be able to do, for example, you may have a circle that looks like this. Well, not really a circle, but you'll have a shape that looks like this. And this will be a circle that's had a section cut out of it and a section cut off the bottom. And you would need to be able to work out the perimeter of this section here. So basically that would require you to measure that length, this chord length in there. Sorry, yeah, chord length in there, that one there, and then that radius again. And if we were working out the area, we would need to work out, we'd need to subtract off this one up there, or we'd need to work out the full circle, subtract off that area up there, and then subtract off the one down there. Now, I think that in the practice questions that I've assigned that are due next term, that I've actually got a question where you're needed to do that. So we should be able to do that with what we know. So those are some examples of the kind of stuff that we need to be able to do. Okay, now let's have a look at the next one. Now this next section on trigonometric functions, I'll just move that back up there actually. If anyone wants to have a look at those, you can pause it and take some notes based on that. Here we go, trigonometric functions. Now this is the unit circle definition using radians instead of degrees. And this is actually pretty much what I was discussing before. So basically you need to let's get that in there. There we go. So you need to be able to recognize that all of these things here that are basically 30 degrees, that is 1/6 of the way to half a circle, so we'd consider that pi on 6. We've got, if we have the equivalent one over there, 150 degrees, that is 5/6 of the way to a full circle, so that'll be 5 pi on 6, and so on. So basically that's, so this is basically just using radians instead. So the unit circle and how we can use it to work out our various things. And then we've got exact values. So exact values are very important. Now when we're talking about exact values, we're talking about, and I'll write them out here, sine theta, cos theta, and tan theta. And our exact values are basically, and we need to be able to work with them in radians as well as degrees. So we should know our exact values in degrees. Let me just draw this. But I'm going to write our exact values in radians up here now. That's 0, pi on 6, pi on 3. Actually, we'll need a bit more space. And that'll do. So, I'll do these in green. We have 0 up there. Now, this would normally be 30 degrees, but that is pi on 6. 45 degrees is pi on 4. 60 degrees is pi on 3. And 90 degrees is pi on 2, because this is half a circle. This is a third of a circle, a quarter of a circle, and a sixth of a semicircle, rather. Half a semicircle, third of a semicircle, quarter semicircle, 1/6 of a semicircle. And we need to know all of these numbers. It's 0 for that one. It is 1 on 2, or half for that. But I won't use that one. I'm going to use green again. So we've got 0, we've got a half. We have, what is it, root 2 on 2. Sometimes it's 1 on root 2. Both of these are equivalent. So they're the exact same thing. Root 2 on 2 and 1 on root 2 are the same thing. We've got root 3 on 2, and then we got 1 to finish off. For cosine, we go backwards. 1, root 3 on 2, root 2 on 2, or 1 on root 2, either both equivalent. This is a half, and then that's 0. Remembering that tan theta is the sine theta over cosine theta, that is 0. That is root 3 on 3, or 1 on root 3, both are fine. Then we've got 1, because it's the same thing on top of itself. Then we've got square root of 3, and then we've got undefined. It's undefined because dividing by this cosine theta being 0, dividing by that gives us an undefined answer. You can't divide by 0. So we also need to be aware of what happens when these get over 90 degrees, or pi on 2 radians. This one would end up being, if we ended up at 2 pi on 3, or 120 degrees. What happens if we end up at 3 pi on 4, or 135? And what happens when we end up at 5 pi on 6? The trick is that these two will add together to equal pi, or 180 degrees. So, but in each of these cases, the sign doesn't change, but our cosine will change. And then obviously, if we've got pi on that side, that will change there. And our tan obviously changes as well. So those are ones that we have to think about. And we may end up with situations where we've got angles greater than pi, or pi radians, or 180 degrees. And I'll be looking at those in a bit. So we'll be able to, well, we'll be looking at those next term. Okay, so I hope that that's clarified the kind of stuff we were doing in trigonometry. And I'll stop it there for now. But I strongly encourage you to have a look at the exam questions. But this is just really a rundown of the kind of stuff we need to know. Just to go back over it again. We had those ones there. We had our circular measure, radian measure. There are lots of examples in chapters 1 and 2 in the textbook as well. And we had our cosine and sine rules. So tomorrow I'm going to be looking at, well, for our next lecture, we're going to be looking at some of the components to do with our linear algebra, and probably get into some quadratics as well. Oh, wait, no, we'll get into functions is what we'll get into. So we'll do our functions and have a look at linear algebra as well, so we can get a good understanding of the kind of stuff we need to know for those. So have a great day, and I'll see you around.